So, in the last chapter 2 days ago, I told you a little bit about classical mechanics. Now we will go just the same way Max Planck went, starting from classical mechanics and coming out in quantum mechanics. This is where it started. Black body radiation. From classical mechanics, the Rayleigh-Jeans law has been derived, and this works pretty fine unless we are reaching high frequencies of light, so which means short wavelength. What's happening there is that we just go up exponentially in the intensity.
What is beam?
This is the intensity. So what we see is that we are totally wrong when it comes to intensities. This is the so-called UV catastrophe. So obviously we are facing a problem. Max Planck solved this problem with this law. You see, this is the classical theory, this is the Rayleigh-Jeans law, and this is Planck's law. We know this curve from any light emitting source when we emit a spectrum. But the question is, how did he get this law? This is the beginning of the journey. Well, actually, we know more than Max Planck did at this time. But let me start with something very simple. The free photon in a box of a certain length. And now the photon must be a standing wave. And to be a standing wave, its wavelength must fulfill this condition. N is any natural number, and L is the length of the box. We cannot form a wave unless we meet this condition, right? Because the wave must be 0 in its amplitude at the one end of the box, and it must be 0 at the other end, wherever it faces the ends of the box. So this is the only way to achieve this.
So we only have standing waves?
Yes. In 3 dimensions, well, the energy is a little bit more, a little bit different. Depending on the wavelengths, we can get the energy. And we are counting the number of photons, which is R. Each photon has a certain energy. We have some kind of 0-point energy, and this here is the full energy of the system. As we are 3-dimensional, we do not have an x, and y, and z, but such a vector of the squares. This is a norm of the full vector of n, x, and y, and z. This is what we are facing. So in principle, we now have a bunch of photons moving in a box. With exactly, it is a cube, because we still consider the length of L. So from there, we can go to statistical mechanics. Nothing quantum mechanical, just pure statistics, and we get a probability distribution. To make things easier, we introduce beta, which is 1 divided by kBt. Kb is Boltzmann's constant. Yes?
What is this Z beta?
this will come. This is the partition function. Okay, so it's just pure classical mechanics with a partition function z beta. We go straight forward. E to the minus 1 by k dt, all energies divided by 2, divided by 1 minus exponential of the same stuff. We know this from statistical mechanics. So it is nothing new. It is still simple statistical mechanics. And if we are there, we can ask ourselves, what is the average energy of the system? The expectation value is called in quantum mechanics, but we just call it the average. Well, we have a partition function, so we can go straight forward. Derived by temperatures. Because we remember, beta is 1 divided by kT. So actually deriving by inverse temperature. And this yields such a nice expression, some kind of offset, plus this. Again, we simplified our things. The energy of the photon is now simply summed up. We just call it epsilon, so that we don't have to write this large sum all the time, this large square.
Just one quick thing. How many of us have seen statistical mechanics before? So quite large number of people, right? Good.
But in principle, this is not difficult. This is really the very beginning of statistical mechanics. So any textbook, if you want to look it up again, or for the first time, you will find these. Now, if we have, sorry, this should mean 8. So this part here, this reminds oneself of Bose-Einstein statistics, which is not so surprising because photons are bosons, so they should follow these statistics. But without knowing this, we derive the correct statistics. And we've just worked classical all the time, or almost, because this is the only thing which is not looking so classical. We have such a number n here, which looks like a little strange. I mean, we have n, which means we can only work with multiples of 1 by n. Or in the energies, with multiples of this total vector, norm n. Now we continue with statistical mechanics. We get some kind of density of states. We just integrate our statistics with some function g over all the possible energies. This is also straightforward. We are still in terms of energies, which is a little, say, one is not so confident with energies because we had a spectrum of the frequencies. But the good thing is that frequencies are closely related to energies. We just need to divide by some kind of length, which we're doing here. We divide by the volume, and we get it in the frequency domain. And now, the only thing that's left to do is come back from density of states to the emission spectrum. Here we need to, well, we are working with photons, so how fast can they travel? What time? Sure, with light speed, c. And we are irradiating our surroundings, and we're doing it spherically. There is no preferred dimension. So the full angular integral of a sphere is 4 pi. is all we need to correct for. And what we obtain here looks like something we've seen before. Because this is just Planck's law. What I wanted to show you with this is that by introducing such a quantum condition, we obtained the correct description. Now the question is, why did it fail? Why does it only fail the original classical law of radiant genes for very high frequencies or short wavelengths? And this is because the wavelengths are short. Now we are below the microdomain. We are below the mesoscale. We are in the nanoscale. We are in the region of atoms. And in the region of atoms, this needs to be taken into consideration, that we have our quanta.
Originally, Planck did not discover it in this manner, right? He had just written the equation.
He just started with all the equation and went through all this statistical mechanics as we had it here. So his only assumption was, okay, let's think of photons as a standing wave, because otherwise he couldn't find any solution. He himself was not so happy with the solution, because it is no longer classical physics. You do not have to continue. You're working with quanta. So he used classical mechanics with a little different boundary conditions, and he landed in quantum mechanics and destroyed the foundations of classical mechanics. Just what I presented you here has been presented shortly before Christmas in 1900 at the Physical Institute of Berlin by Max Planck, which was the very first talk ever on quantum mechanics. And yeah, at this time, let's say it didn't have many fans. So they were all very upset.
But these are all after what Boltzmann wrote about the statistical mechanics.
Yes,
So he
yes.
knew completely statistical mechanics.
Exactly, the statistical mechanics were totally known. Boltzmann had published all his work at least 20 years before that. So he could rely on the foundation of statistical mechanics. And in principle, in quantum mechanics, we are in a very statistical world. There is no yes. Sometimes there is a clear no, but there is no clear yes in quantum mechanics. Only a probability. So, coming from there, one doesn't always want to go all this complicated way. A more straightforward approach, like in classical mechanics, like Hamiltonian mechanics or Lagrangian mechanics, would be much preferred, wouldn't it? I mean, we don't want to see, okay, let's see, can we find any new boundary conditions and then go through all the way through statistical mechanics. And Schrödinger tried to solve this problem. So what we've seen, we worked with energy. So obviously, a Hamiltonian look on this problem may be a good idea. We know from our Hamiltonian, it is kinetic energy plus potential energy. So nice so far. What we also know is the Planck-Einstein relation connecting frequency and energy. E is h times nu. H is a proportionality constant. What Planck found, later they found out it's a natural constant. And also we know from the special theory of relativity that E is m squared. Well, we can combine. If E is h nu and m squared, then m squared is also h nu. principle, but this is a little bit surprising, because we can now relate mass to frequency. More interestingly, photons should have no mass. They're traveling at light speed, as they would have a mass. According to the general, even to the special theory of relativity, their mass would be infinite at light speed. But we can show that they have a mass. Obviously, they only have a mass when they are moving. But we can find their mass just with a frequency. Two constants times frequency, and we get a mass. So this works. Why not relate frequency to a mass as well? So we have a mass related to frequency. Now we go the other way around. And this is what de Broglie did. Any particle, typical properties of a particle is mass and no wave behavior. So even a point particle assumption is valid, at least for small particles. Can be described as a wave with the properties frequency and no point mass. I mean, a wave is something that's valid. And vice versa. So every particle is a wave at the same time. Every wave is a particle at the same time. And as such, we can assign a wave function to any particle. This is the first step towards Schrödinger's equation. Only problem is, how do you obtain the correct wave function, right? So we know it is a wave, but we do not know its wave function. Let's see what we know. What we know is that the wave function should determine the energy. The wave has a wavelength is connected to a frequency to the energy. So we know that if we precisely describe our wave, we also have a precise description of the energy. It should be linked. And from linear algebra we know that in this case you must find an operator which yields the correct energy when acting upon this wave function. So operator acting upon the wave function must yield the energy times the wave function. We can even say more from linear algebra. We can say that in this case the wave function is an eigenfunction to the operator, and the energy is an eigenvalue to the operator. These are unique functions and unique values linked to each other. And they are both the representation of this operator. If we have this operator act on a set of different functions, only one of them is an eigenfunction, then we will only get the eigenfunction with the energy. We know this from something similar when we're dealing with matrices and vectors. You know that each matrix can be brought to its diagonal form, and then we obtain a specific set of vectors. It's just the same, but in this, now we are not using a matrix but an operator, and not a vector but a wave function. But in principle, there's no difference. So it is obvious as well that this operator must represent the Hamiltonian. So Hamiltonian acting on a wave function is the same as kinetic energy acting on a wave function and potential energy acting on a wave function. But kinetic energy is pulse squared divided by 2 times the mass. So we can deduce that we do not need to know all these operators in its final form. We can build them from the pulse and from the potential. Coming from a classical world, we need to find good descriptions for our operators. Well, coordinates makes coordinates operator, which is the same as coordinates. That's same counts for time. So even if you're in space-time, this works pretty fine. This means that our potential is a potential operator, which is the same as a potential, because it is a direct function of coordinates and time, unless it is a function of velocities. In this case, it doesn't work this way. So note that there are no derivatives here in this operator. As soon as there are derivatives, we need to go another way. And then things are getting complicated. More interestingly, momentum is not that easy. One would think if time and space just stay the same, then their derivatives do as well. Unfortunately, they don't. So here we have the imaginary unit, I. I think you all know, I is square root of -1. And h bar, which is Planck's constant divided by 2 pi. And then we have this differential operator. Nabla is first derivatives of our system. Acting on a field, we obtain the gradient of this field. And yeah.
Good question. So these transformations that you are going from classical to the quantum world, we accept them as given, right? Or do they have
Yes,
mathematical derivation?
But these were easy to derive mathematically. This one, nobody knows how Schrödinger got this idea. Really nobody knows. It's a miracle. Perhaps he was trying so long until it worked, I have no idea. Nobody has.
This is very nice.
But it works. Here's the definition again of H bar. And finally, energy and time-dependent representation. Well, this is somehow the derivative with respect to time of our wave function. This, by the way, gives us some idea on the wave function. It must be somehow linked to action. We know that action is the integral of energy with respect to time. So obviously, the wave function has something to do with action. If combined with Planck's constant. So we obtain Schrödinger's equation. This is directly energy time dependent. This is the Hamiltonian kinetic energy plus potential energy. Little mistake in the sign, should be a plus. And this is the same as energy. I will correct these little mistakes before I upload the slides. And one other nice, very nice thing in quantum mechanics is if we combine many particles, their wave functions simply add. Especially when they are not interacting, but also when they are interacting, because in this case each wave function depends on all the others, but they are still additive. So we are seeing a superposition of the wave functions.
Can I have a quick question about this Schrödinger equation? So the wave function is in terms of time, right?
Yes.
But from this equation, we don't have any derivative with respect to time. It's only with the spatial derivative.
No, the wave
right?
function is depending on space and time.
But I don't look at the first part, the middle part. So
Yes.
I'm combining the middle part with the last part.
Yes.
Because this is kind of later on becoming some kind of
Right,
eigenvalue
right.
problem, right? So the middle part doesn't have any derivative with respect to t.
No.
And then the last part, which is equal to E times phi. So if I'm combining the last two terms,
if you're just working with the last two terms,
Right,
you're getting a static wave function.
So it's static
There's
wave,
no time
so there's not
dependence.
the time on that.
If you combine this with this,
Right,
you
then
only
it's
get
gonna be a
time
different
dependence.
time. But then
So
you're
you
all,
need to have both of them to have the full space-time dependence.
But
okay.
the middle one also depends on t because the potential depends on time.
The
Yes,
potential-
but it is
but
just
you need to
integrated,
solve for
it's not
potential.
integrated already. So you can, we do not,
But you know
these
V.
operators, we do not
Oh,
get any
V, right, not
information.
V. V is the potential? Is
V
it
is
V?
potential
V
and
is
it's
known.
known, right?
Oh,
It
V is
is-
given.
It is known.
V
is given.
known.
But still, in this part here, it's difficult to obtain the time dependent part.
Okay.
So in this part typically just yields our static description.
But then why, if you have many particles, why they can simply just add them together? Is there real, in the physical quantum mechanics world, is this real interaction or not?
No, they, when they are interacting, then the interactions are in the potential.
Or in the potential?
And as each wave function is still an eigenfunction, we can simply add up all the wave functions to get the total wave function of the system.
So then in other words, that V is dependent on the wave function, right?
No, V is independent of it.
It's
We
independent.
just derive very classical. We just take the same potential as we would take in classical mechanics.
If there are two particles, they are like repelling each other through Coulomb, we assume that V scales with 1 over R, right?
Right.
And then we do the calculations, we derive this size, right?
Exactly. So we can just take our classical potential.
So by wave functions, you mean the possible wave functions for one particle, or for example, we have two particles and we have two wave
Then in
functions?
principle we get two Schrödinger equations for two particles. One for particle 1, which is centered in the coordinates of particle 1, and the other one is centered in the coordinates of particle 2. So we are getting them more than one. We are always relative to each particle.
But
So-
will they have the same energy?
If they have the same energy,
If
this
they're-
doesn't matter. Then we just get multiple solutions at the same energy.
But you can only do it because like the entire equation is first order.
Right, right.
So we can basically, for the potential, we can separate the potential of each particle and then treat them separately.
Exactly,
And then add up the wave function.
right,
at
right.
the end.
So what we see is, we have a superposition of not only, well, in principle we have a superposition of the wave function of the particles, which we see, but this is not the full story. Unless we measure a specific state. So without measurement, the system has no specific state. All wave functions are possible. So the system is actually not only a superposition of the measurable wave function of each particle, but a superposition of all possibilities, how this could be. And as soon as we measure, it leads to a collapse into a specific quantum state. A quantum state is a localized wave packet, which is formed from all the wave functions of all the particles. So probably there's always a very dominant wave function, which is the ground state of each particle. But in principle, we are not limited to this. And if we measure different, we obtain a different result. There's a very nice experiment. If we are taking a light source, let's say a laser, we emit light in a certain way. Now what we do is, we are just splitting it with a semi-transparent mirror. Now it's the question, what are we doing? This is our measurement. Double slit in principle. And we are combining. So, typically what we expect if both slits are open is to observe interference in the end, right? Which means that 50% of the light is going this way and 50% is going this way. We agree on this. We integrate over all intensity, we get the total intensity of our laser. If we close slit number 1, this should mean that we only get 50% of our intensity, right? But we get 100%. And if we open this again and close this, we still get 100%. But without interference, of course, because there's the second beam missing. So what we're getting is always 100%. This experiment has been done in reality, and this is the result. So we have these quantum states. We have the full wave function for this way, which we see when we measure only this way. We have the full wave function for the other way if we measure the other way. And we have the wave function combination of both ways, which is our third wave function, which we measure if we have this experiment this way. So in the quantum world, you should be very careful in what you measure, because your measurement determines the wave function you see. If we don't measure at all, we have a superposition of all three wave functions. So, as you see,
So, excuse me.
yes,
The intensity of the light depends on the size of the wave function. I mean,
no, you mean it's just the same intensity as the laser should have in the beginning, minus
So-
the typical losses.
how is that related to psi? I mean, the
Um,
intensity.
This is, of course, related somehow, but the thing is, we get an amplitude for each psi, and normally in a laser we have more than one photon. So we just sum up over all the photons which are going through. So if we have an intensity which should be related to 500 photons, then it's because we have 500 photons.
So the intensity comes from the wave function of each individual
Yes,
one.
yes, and we are summing up. Yeah? Just as I here. It's simply added. So we are just summing over.
Can't we have a wave function that contains two particles? The positions of two particles? Can't we have a wave function that
Yes, sure, we can have
Yeah.
one which we can we sum up, so we have the full system wave function. We do not see the individual wave functions. We see their superposition. We never see the individual one. So what chemists like to do to visualize their orbitals, to say this is the maybe 1s orbital of hydrogen or something like this. Well, for hydrogen this is actually true because we only have one electron. But for all of the other atoms or even molecules or crystals, this is no longer the reality. We can, of course, say, okay, these should be parts of only one electron, but we can never measure them. We can measure the total superposition of the entire wave function. Or actually not even this, we measure the probability distribution, which I will show you. Because this comes here. Because the wave function itself is not an observable. We cannot measure it. What we can measure, however, is its square. This is the probability distribution. So this is the density function. This density is the square of our wave function. This is what we can measure. Actually, we only see it of the entire system. We cannot say in an experiment where we measure the, for example, electronic density of hydrogen molecules to say, give me just the density of the electron that comes from hydrogen number 1. We see the total density. We can ionize when we see a different density, but the difference between those is still not the wave function of a single one, or of the one which is missing. Because by ionizing, we are removing an electron. If you remove an electron, they do not face the same potential anymore because the coulombic repulsion between those is missing. So we can only measure the system as a whole. We can never measure a single part of this system. As soon as we remove a part from the superposition, we change the entire Hamiltonian. Unless we have non-interacting particles.
Basically, you are saying that we cannot do any kind of calculation if a particle is created, like a grand canonical black one.
No, we can do the calculations, but the question is, do they have any observables which we can measure? We can only calculate our entire system as it is. Sure, we obtain orbitals and we can explain quite a lot with it, but physically they are not measurable.
But one thing, when, for example, if you excite like a particle and you can observe that change because like chemiluminescence or whatever you are observing, you know that the orbital has changed there. So can you relate
No,
that?
you know that the
observable
total
change?
density has changed,
Okay.
which we relate to orbitals, which we obtain from our calculations.
Okay.
But actually, it is just a change of density. Unless we have only one single electron. Then we can say for sure. So, we have our density, and to find it within a certain volume and time interval, we just need to integrate our density in the correct boundaries of time and in the correct boundaries of space. We can say at which probability we find it there. What we always know is that this particle exists. So it has to be found within our universe, which means all space, all time. We integrate over all the time, over all the space, and we know that the integral of the density must be 1 for one particle. If you have a system with 10 particles, the integral of the density must be 10. If we have a million, it must be a million. So what we know is that our wave function must be normalized. So that the integral of its square is 1. This is very important because typically, so nice our mathematical solutions are, if you forget to find the right factor for normalization, we are obtaining totally wrong results. Here, we are obtaining wrong results. Okay, so we are all of a sudden having 1.341 particles in our system where there should be 2, which is because we forgot the normalization of our wave function. This one is very important. From there we get another one. We know that wave functions are additive. And we know that for two particles the integral should be 2. So we are adding our wave functions, and then we have the square. If I just multiply, please remember that wave functions can be complex. And as such, we have complex conjugate with non-conjugate plus non-conjugate plus times conjugate. And this must be 2. Well, this is a sum of integrals. We know that these integrals are easy to solve. But if each of them yields 1, then the remaining part must be 0, which is only fulfilled if this holds true. Now we also know that these are observables to density. Observables written in such a matrix of different wave functions must be in a Hermitian matrix, which means that we are having a symmetry with respect to the diagonal. So these need to be 0. That's the only way to fulfill it. And this means that whenever we have two wave functions, then either they are the same wave functions, and then their integral is 1, or they are different, and their integral is 0. This is Kronecker delta. Of course, this only holds true if the wave functions we found are true eigenfunctions of our system. I mean, if we did not find eigenfunctions, then this doesn't hold true either.
So you are saying that the eigenfunctions are very similar like eigenvectors that we had in math.
Exactly.
They should be normal to each other.
Yes?
So basically the integral from minus infinity to infinity of their multiplication should be 0.
Yes.
You know, it has some similarity between eigenvectors of a matrix being normal to each other, right?
Exactly. Exactly. So we have an orthonormal basis.
Do we define our basis set, I mean these eigenfunctions to be normal, or they turn out naturally that they are for normal?
They are orthogonal by nature, because this is already in the Hamiltonian. So Schrödinger's equation always yields to orthogonal eigenfunctions. Always. With the exception of user error.
What is the physical meaning of it?
The physical meaning of this is that, first of all, not just the wave functions are additive, but also the densities. So that the total density of the system can be derived by summing up over the densities of all the wave functions. So this in principle would yield some kind of possibility to measure the effect of each particle, if you could get this measurement without removing it. Because typically we have interacting particles. So removing one changes the entire interaction, thus changes the potential energy. The other physical meaning is that in principle, whenever we are doing things like exciting, going to another state, that the excited state does not directly interact with its ground state. So that the wave packages are typically well separated. Things change a little when we have interactions together with other particles. Then of course you can couple, but there's no direct coupling of one particle in its own states with its other states.
So the wave function is it a scalar function or is a vector function?
You can form a vector space, some kind of vector space.
The one you are talking about in the
But
previous
these are typically
Scalar.
functions.
scalar function, right? Okay.
And then you can form a kind of space, vector space, which contains all these functions, which is then the Hilbert space. But yeah, principally they're scalar. So let's go for some examples. Maybe a simple one. A particle in a one-dimensional box. So, how do we make our box? We say it has a certain length. It starts at a length of 0. It ends at a length of L. Inside the box, we have no potential. Outside, we have infinite potential. So, what we have is something like this. V x, say 0, L. Okay, so infinity here, infinity there. 0 in between. So as long as our particle stays inside the box, it faces no potential. It is a free particle. If it wants to get outside, it will need infinite energy, which it cannot get. So it either stays inside or not. But not means to annihilate the particle. Let's look at the time-independent part first. We have no potential, so we just have kinetic energy. You know it is minus h bar squared divided by 2m, and it's the mass of the particle. Second derivatives, our lambda squared. And now I just called this wave function a little bit different to distinguish between time-independent and time-dependent parts. And this should be the energy. So obviously this reduces to something which is telling us we need a function which has second derivatives which are the same function multiplied by a factor. There's not so many functions of this kind, and this is the easiest one. We just work with a linear combination. In the beginning we do not know if it is a cosine, if it is a sine, but this is linear combination. It works. A and B can be complex numbers, don't need to be. They just need to be fitting. We later get them from the boundary conditions. So regardless which of both we have, we can then obtain our energy. H bar squared divided by 2m is what we had in front of. Then we're looking sine of kx. First derivative, cosine is k times cosine of kx. Second derivative is minus k times k sine of kx. So it's minus k squared of sine of kx times sine of kx. So this is our k squared, and this is why we don't have a minus anymore, because we have minus times minus. This was easy one, huh? Pretty simple system. Couldn't we just have this k? So next, the time-dependent case. This is our operator. We have chi of t. Real function which yields itself times a factor after derivation, plus the second constraint, because we have a complex operator here. It must be real if we can observe it. We can also say if this is real, it must be real. But to be an observable, it has to be a real number. Well, okay, so this should do the job. Derivative is minus I omega times the same function. I times I cancels out because we have this minus in front. So we have I minus I squared, which is minus minus 1, which is 1. And we get a nice expression for our energy. Our wave functions did not share variables yet. So we can simply multiply to get the full space. It's the same particle, so we can multiply. And different coordinates. This is a very simple product ansatz. Don't run when you see these nice German words in quantum mechanics. You will find them everywhere. Quantum mechanics has been mostly, well, not mostly, but to large parts being developed in Germany in the 20s. And even international journals publishing in English had the quantum mechanics articles in German. So it was a pretty German community. So all these words still stay in quantum mechanics. So we do not call it approach or whatever, we call it ansatz. With this product, we get our full wave function. What we can see is this is a vibration, and this is some kind of damping. In principle, something that looks a little familiar, right? And we know that those energies need to be equivalent. We had the T plus V part and we had the time-dependent part, both are equivalent. So in principle, we can write omega equals h bar k squared divided by 4. Now all what we need to find in the end is a nice expression for k. Have a look at our boundaries. We know that the particle can only move within the box. We know that it has to be 0 in the boundaries. So this is the only possible solution. And finally, we normalize our wave function. We just run the integral, wave function, complex conjugate times wave function, integrate it, look what number we get, and divide by this number. So the integral is L time divided by 2. So the normalization factor is square root of the inverse. Square root because we multiply the wave function, right? It's the square of the wave function. So we need the square root to get the correct normalization for the wave function. What we found here is interestingly the same Max Planck found for the photon in his black body radiation winding experiment, right? Remember this? We had this in the beginning. This is where we started. And this is what we derived, but this time with a much more elegant formalism. From there we can do the statistics and obtain the same result. Pretty simple. What we can do is to have some looks to see what happens when we play a little bit with dimensions. So number one, what we see is that obviously this quantum number is quadratic in it. So the higher the quantum number, the larger the distance is to the last energy level we reached. At the same time, we see that it is divided by the length. So this also gets quadratic. The longer our box is getting, the lower are the differences between the energy levels. If we go to infinite length, we obtain a continuum. This is a macroscopic limit quantum mechanics. the length is getting large enough, it looks macroscopic. So quantum mechanics is a smooth theory. It can bring us all the way up to macroscopic systems, where we can work with classical physics. Which is nice to know, because this means that we do not face any strange behavior when we go to the mesoscale quantum mechanics or something like this. It just becomes the mesoscale very smoothly.
So basically you are saying that as L grows, the difference between these energy levels becomes very, very, very tiny, such that if you are at really large scale, we do not see any effective change in the energy.
Exactly. Then we are just
That's
running
good.
continuously. So we've computed wave functions. Let's have a look at wave functions. What we see is, this is our box. Here in the boundaries, we are at 0. And we see this length. Here, this is the first wave function. Nice to see. It's a half sine in principle. The second one is the full sine. Then we get 1.5. And then we get 2 full vibrations, which is pretty nice. I just put them all on the same note so that you can see and compare. Much more interesting is to look at their square. So this is the probability to find a particle. With n equals 1, well, this doesn't look exactly as you would expect from Newtonian mechanics, does it? I mean, look at this part in Newtonian mechanics. You have 2 walls and a particle in between. We do not think of any losses mechanically, so it is ideally moving. It just keeps its kinetic energy, right? It hits the wall gets twice the impulse, particle is reversed, hits the next wall, and so on. This goes on forever. If we integrate this, if you want to see where we are at any time, we are obtaining this probability. The same probability at any position. And now we compare already with n equals 1. This is a totally different picture. And it gets even better when we go to n equals 2. We have a total 0 probability to find it in the middle of our box. This is definitely not what we expect from classical mechanics. Such a thing we call a node. And this is a very important characteristic for quantum systems. Wave functions have nodes. The wave function changes its sign at a node. The probability is a clear 0 at a node. So we will always find nodes in quantum mechanics. Or something like this. I mean, this is pretty interesting, isn't it? We're having a particle. It is moving. We are using the classical potential. We're using the classical boundary conditions, and we're obtaining this result. Now, if we want to go to the classical limit, we of course have the sum of a very large number of probability distributions with infinitesimal energy differences, so easily accessible. And if you sum over all, then of course we get a flat line. You just take the integral over all n, the full density of states from 0 to infinite. And then we have a straight line. If we look for the average place, by the way, the average place is classically in the middle of the cell, and quantum mechanically as well in this system. It is just x times probability integrated out with respect to x. And then we are always landing in the middle. Which is funny because even for n equals 2, our expectation value of the location is in the middle. Also, we cannot find it there. Quantum mechanics is different.
So one thing, if we put a very large number for n,
Yes?
so it becomes something like a uniform,
We get many, many, many oscillations then.
right?
Yes.
Does it behave like a uniform thing, or it has many, many, many nodes, right?
It has many, many nodes. So it's hopping hopping over the nodes, more or less.
Do they have the same amplitude?
Here they have the same amplitude, yes.
Even if it's, for example, 10,000, it's all.
Okay, yes, because it's just normalized
I
by
see.
square root of 2 divided by n.
So as n is lower, the uncertainty of where it's located it becomes higher.
Yes, yes. And well, of course here we know pretty well where it is located, right? More or less around here. So we can just work here, we can work with some kind of 6 sigma. Find it, but here there are 2 already. So we have a large n dependence on where to find it until we reach the classical limit. Let's look for a second one, more challenging. The harmonic oscillator. Such a nice little potential and such an evil Schrödinger equation. We need a function that fulfills all this. This needs to be an eigenfunction to this operator. Yes, so we should obtain only the function times some constant. The good thing is, things like this have been solved 100 years ago, or 200. Mostly by some French mathematicians who hadn't anything better to do. So, this looks somehow similar, doesn't it? Here's an equals 0. Okay. So we then would bring this part on the 0 side. Well, the derivative of something where we just get 1x would obviously add an x squared here. And this looks like this part. Really nice. Hermite's differential equation. And the solution are Hermite polynomials. They are not orthogonal with respect to integration by themselves, but when you multiply them with a Gaussian function, they are. So obviously adding half a Gaussian function to each does a job. And then we obtain Hermite functions. To make life a little easier, we have our frequency, which is square root of k divided by m, which by the way is the same that you should have obtained with the classical harmonic oscillator. That's your vibration frequency. So, these are the general solutions. These are our Hermite polynomials. This is our Gaussian, and this is the normalization. And here we have a dependence on the quantum number. So this means that the factor which we are multiplying with this is getting lower and lower and lower the higher our quantum number gets. So that our amplitude gets lower the higher we get in energy. But of course, as we are getting broader as well, the full integral over the function still is the same. Or rather, the full integral over the square of this function is the same, namely 1. If we look at one vibration, the probability to find this vibration is 1. So, 100% probability. These polynomials have such a nice recursive relation, but they are not as complicated as it may seem. Maybe we want to get derivatives from here. Nice stuff, but with this easy recursion, we can easily get our derivatives. We can also get the integrals very easy. We just need to change things a little bit, and we have our integrals.
Of course. You remember that you were solving this particle in a box, and you told us that if this becomes really large, it becomes continuum. Can you make the same analogy for this one so we better understand this thing? What's the analogy? When does this
Here-
equation become continuum?
The harmonic oscillator actually, if k approaches 0. Yes. Or if the mass is getting large. Because you always have your omega inside, so when the mass is getting large, you have a very, you're approaching, this is the only way to work with it, large mass or small force constant. That's all you can do about it.
And its wave function basically becomes really flat, right?
Yes, yes.
Okay. Very nice.
With k equals 0, you're directly continuous, regardless if you're in the quantum world or not.
So if k becomes continuum, like 0, it becomes similar to a free particle, right?
Yes, right.
If n becomes large, then
Excuse me,
So,
do we have any real example of this in,
for this harmonic oscillator,
yeah, in quantum world?
it's a good estimation of molecular vibrations.
Yeah.
Here you are just using the second, in principle you're not so much using the wave functions to solve it. What you're doing is to just use this. You're getting the force constant for a vibration. You know the reduced mass of this vibration. And then you just insert this into this part. And you have everything you want. It is not a true picture because you have an anharmonic oscillator, right? Every bond breaks at some time. The good thing with the anharmonic oscillator is that you can get its functions from these. So you're doing a basis set expansion, so you're using many of these to form a basis, and then you make all the matrix elements for your anharmonic oscillator. And then you diagonalize your matrix, and you get proper expansion coefficients for your basis. So for example, 100% of, it would be full harmonic if you would get 100% of n equals 0, and then 100% of n equals 1. But typically you're getting something like 90% of n equals 0, then 9% of n equals 1, and then perhaps another percent of n equals 2. And if you add them all, and you have the square of this, then you're getting your correct probability, and you're also getting your correct wave function, which is multiplicative then. The thing with this is, as soon as you use an anharmonic potential, these functions are no longer eigenfunctions. So they are no more orthogonal for an anharmonic oscillator. So as soon as you add something as simple as a cubic term to your potential, this is no longer an eigenfunction.
So obviously this is a way to solve your previous differential equation, the one-dimensional
Yes,
Schrodinger
yes.
equation with that's potential equal to something with x, right? I guess instead of using this way to solve the problem, if you go back to your previous slides, if we can, the previous one,
Yes,
yes, look at the H2, that's the equation, right?
yes,
So this is a very standard differential equation. We can
Right.
use many other approximate ways to solve. We can discretize this one
yes,
simply using finite element, for example, right?
yes.
So I guess the reason you show that in the past, the computer power is not enough.
Exactly. This has
Right.
been solved in the 20s.
Right. So now the question is, if you were asking me to solve this problem, I'm not going to use the Hermite function. It's kind of a specialized function, right?
Yes.
So I can use the finite element method to discretize,
Sure, of course.
so
You
it's,
can
that's
also use
doable,
Monte
right?
Carlo.
Yeah,
for
that's even,
example.
yeah, sure.
So it's yes.
Yeah, because
Nowadays
just from
it's
the differential equation, well, it is hard to guess, but yeah, that's
But is it really advantageous? Or-
using what?
The analytical solution is faster, of course, but on the other hand, once you have a solution, you can work with it.
No, imagine that you have a more complicated function, right? Which we cannot solve it using these Hermite functions. Then, what do you suggest? Is
Then-
finite element a
Yes.
good solution, or we should go and use basis sets? So it
Well,
becomes more
depends.
advanced question, right?
Sometimes we can use basis sets, but we can also use finite elements, whatever. We just need a proper grid for our computations. So there are some groups who are just working with completely numerical methods nowadays to just directly guess the electronic density of a system. So they do not even solve the individual orbitals.
So basically, brute force finite element from the very first time,
Yes.
right?
Yes. For example, if you look at a group of Axel Becky at Dalhousie University, he is currently just working directly numerical.
And
To
that
get
is
the
good.
direct density out of it. But I think he is using a Monte Carlo based algorithm.
Is there any pros or cons for it? I mean, like in terms of computational expense?
Computationally, well, yes, of course, the analytical solution is faster. This is the advantage when you're going to very large systems. But
My own feeling is that then if you use, for example, the functionals, things become much faster, right?
yes,
In terms of convergence, rather than doing brute force, that like finite
Yes.
element that scales with n cube, right?
plus we have derivatives much easier. I mean, we have an analytical expression, we can get analytical derivatives. So if you want to have the gradients of the wave functions, you can get it here analytical. If you have a numerical grid, you also need to have numerical derivatives. So this entire process is getting more and more, more and more complicated. But in principle, with modern computers, it's not that much of a problem. One finds a nice way to store all the information. The numerical method can be much faster than someone trying to solve the problem. Finally, we see the energies, and we see they are linear with the quantum number. So this means the difference between two energy levels is all the same all the time. And it is all the time h bar omega. This is the difference between two neighboring quantum levels. Or to get a little closer to Irvine's equation, you know there was some 2n part. You can formulate it like this. You will directly see how it's linked. So this one's easy. Now we have the wave functions. I just have their respective energy levels as a line, and the wave function directly plotted on top of it. So here, something should directly catch your eye. With our particle in the box, we were 0 where it hits the potential. Now look at this. Here, the wave function of n equals 0 should hit the potential and become 0. And it isn't, right? You see this? We have density where there should be none, outside the potential. Should it be 0? Classically, you build a ball. Should your particles be in the ball?
No, it means negative kinetic energy, which is
Yeah.
positive.
Right, but here we have it. It's inside. This is a real quantum effect. This is different in the quantum world. And this effect we call tunneling. And tunneling means that in general, unless we have a special case, the probability to find a particle outside its potential is not 0. We are using this for technical applications. Scanning tunneling microscope. The tip is not in contact with the surface, and still we get a current because we are tunneling. Or another nice way, perhaps you know it from nuclear physics. You have a nuclear core with too many protons, and one proton reacts with an electron to form a neutron. Well, this can happen because the probability to find the electron in the nuclear core is not 0. So in principle, with a certain probability, the electron had been there all the time. And the rate for this reaction is simply determined by the probability. So here is the first real quantum effect that we see, tunneling. And we find it in many systems. It's not only that you need very small particles like an electron for this. Hydrogens can tunnel. Hydrogen atoms can tunnel pretty fast. You can see this in water. When you're using heavy water, you can see that it doesn't happen. So the conductivity of heavy water is much lower than that of water, because deuterium tunnels at a much less probability than hydrogen. Twice the mass and square root of 1/2 of the celerity. So this is one of the most important effects that we have in our quantum world. Something that is totally non-classical.
So, can you explain the vertical axis of the previous slide?
Oh, sorry, shouldn't be, but it's V of x for the potential, and it is the problem. It is actually the wave function is dimensionless.
So I could like scale V of x in a way that to make it feel like I am
No. V of x is of course scaled with respect to its energy. So if I scale V of x larger, then these differences would be larger. Because these are the real respective energy levels. And in principle, at each energy level, you start with a 0 and go up to plus minus 1 for each wave function of each particle. The black one is only the potential. This is true in energies. It starts at 0 and it goes to infinity. That's 1/2 kx squared. In this example, I had simply k equals 1, m equals 1, h bar equals 1. So just to have a nice figure. Okay. And you also see that this tunneling effect is not just little k, right? I mean, look at it, how much space it has in the potential and how much space it has outside. And finally, something else that should catch your eye is you have an idea of entropy, right? Something like when you approach 0 Kelvin, you should have 0 entropy, which means 0 movement. So look at this. We cannot reach 0. This is the first energetic state. Our vibrations cannot go to 0 on the quantum level. Our phonons, which is kind of vibrations as we know, cannot become 0. So even at 0 Kelvin, there should be movement. And if there's movement, there's entropy. So it is impossible to reach 0 Kelvins. You can approach closely, but there will always be this 0-point vibration in any system. You cannot avoid it. You can't freeze. All exhausted or?
That was great. I love it. I love it.
I mean, if you want, we can also briefly go through uncertainty directly on the board, because I like to write this on the board. If you want, it doesn't take long. We just need our operators.
We are running out of oxygen in this room, right? Let's open the door. Fresh.
So, simple thing. We remember.
Can you use another color? I mean,
Okay. Oh, I can use the blue. Let's just look at this. We can measure two observables in quantum mechanics if their commutator is 0. So what is a commutator? Well, if we have an observable operator 1 and another one which is 2, then their commutator is just, oops, of course without it, product O1, O2 minus product O2, O1. Should be 0 all the time, shouldn't it? But of course, it is not. Because they are not standing alone. They have a wave function on which they act. So it makes a difference if O2 acts first on the wave function and then O1, or if O1 acts first and then O2. Or it can. So let's have a look at some nice commutators. Simple one, X, Y. Any assumption? Can I measure the X and Y directions at the same time? Well, let's see. This is xy minus yx, so they're simply multiplicative. So if there's a wave function or not, doesn't matter. It's zero, sure we can. Much more fun. Px and x. Where it is here. In this case, I write it out with the wave function, which makes things a little bit more obvious. So, this is Px, x, psi of x, minus x, px, psi of x. Everybody remembers Px?
Partial. Or partial x. IH.
How the operator is?
Minus IH. No, minus
Yeah.
minus IH.
Minus AH bar, and then, of course, dx. Okay, so this is then obviously something in front of it, minus AH bar, and then okay, I think I don't need to solve this because you directly see what's happening, right? This is a product where we need its derivative. Or I can just do so. I like the fun. IH bar. This is then prime of x times x plus psi of x minus prime of x. Well, this is the same, the other one not. Yeah, right. What we remain is, well, this is not zero.
It has IH, right?
Yes, this IH bar. And this is what all these commutator pairs do. PY, Y, PZ, Z, they are all yielding IH bar times the wave function. What?
So what's the meaning of these coming?
This is the uncertainty of our measurement. So this means we cannot get the pulse with a higher accuracy than this if we at the same time measure the location. We cannot say how fast and where a particle is at the same time. Not for sure. This is our uncertainty.
So I should probably go one step behind. We should accept that this commutator gives us the uncertainty, right?
Yes.
We accept it.
Yes.
If this
I
gives
mean,
us
this is the we have to accept. We don't have another choice, do we?
I don't know.
Okay, actually it is minus IH bar, by the way. There has been lots of discussions of the early school of quantum mechanics what this means, really. And they believe that this is the price that we are paying for being not able to really understand the quantum world. So this is the amount that comes from our non-existent total knowledge of the quantum world. If one would find a more precise theory for the quantum world, perhaps the uncertainty relations would vanish. But from our knowledge of the quantum world, we cannot get any closer to it. So this is one important commutator, the pulse and the location. And the other one, which is very important, is of energy and time, where we obtain IH bar and not minus IH bar. But still, these are very important. And the energy and time, this is a very, very important couple. Think of femtosecond spectroscopy. So we have a femtosecond of delta T. Right? So what we can say is delta E, delta T must be greater or equal to IH bar. Well, this means, so what do we see here is, the smaller we get in our time domain, the larger we get in our energy uncertainty. With a femtosecond laser, we have quite an energy range which we cover. This means that we can get non-resonant excitations. We do not need to hit the resonance, we just need to get close enough to delta E. With attoseconds, it's even more easy to hit any level. But they are not stable for long. Then the time dependence gets to full measure, and we're losing the state pretty fast. These are the uncertainties.
Long lecture.
Okay. Next Tuesday, we'll continue with the hydrogen, atom, and many body systems.
Any homework? Anything?
Well, you can compute a couple of commutators if you want.
If you give out homework, I'm gonna distribute it through the email, right?
I mean,
Did you guys do the homework for the
Last session?
sorry?
For the last session,
Yes.
half of it.
Half of it? So should we like collect the homeworks, or? I mean, like, this is a pretty relaxed course, right? This is not one of the courses that we're gonna grill you for handing in homework. It's very important for you guys to come here motivated and get things done and take part in discussion and improve your learning, right? This is very high level, like graduate level course.
and the homeworks are to help you to get a little bit more used to it, to understand it, to get a deeper understanding.
Then they're gonna put a lot of weight on the final project, right? So you get your hands dirty with actual calculations.
Perhaps some nice homework that you can do for once. PXPY is a very nice. PXP, P is then the sum, PX plus PY plus PZ. And to make things easier, this one as well.
How about PX and X?
PX and X we already had.
PY and X?
Yes, and this is other things we can do. Which is then P X and Y. PX and R. Where R X plus Y plus. And finally, just to have some more fun, this is a nice one. Oh, and of course, some combinations of Hamiltonians. Here you take, of course, so in this case, This is not the time-dependent Hamiltonian. This is a time-independent. And you look what happens together with kinetic energy and together with potential energy. For potential energy, you just take the harmonic oscillator. So we equals okay squared. Then you're getting a feeling what is uncertain and what not. So this covers almost everything.